Okay, hello everyone. Let's start today's discussion. Today we are gonna go over some examples, so we make sure that we are clear on the Locus method, how to sketch the trajectory of the poles, all the techniques that we said, how to find the interception asymptotic lines, breaking breakaway point, crossing the imaginary lines, how we can find them, and uh, how we can design our system for a specific, for example, damping coefficients. Okay, let's start our first example by having the open loop or forward pass transfer function as 1 over s plus 2 and s plus 5. Now, for the Locus, we said what we want is to have a negative feedback of that open loop function. In this example, we are going to consider a unity feedback, and the general transfer function of our feedback loop is going to be the forward pass over 1 plus forward pass times feedback loop pass, which is here is 1. Okay, so if you solve this formula and find the transfer function, we are going to see that our transfer function is going to be k over s squared plus 7s plus 10 plus k. Now, I assume you already know how to find these and derive these mathematics. We just put the g of s in the formula and solve for the general solution and general transfer function. Now, we want to sketch the trajectory of our poles. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. That's enough. So let's run the analysis for sketching the trajectory of the pole based on the Locus. The first step we had was to place the open loop poles and zeros on the S plane. Okay, so we don't have any zeros, so we don't put anything as a zero. Then we have two poles, one at -2 and another one at -5. So we are going to place them 3, 4, 5 on the S plane. Now, next step was to find which portion of the real axis is part of our trajectory. And the rule was for the negative feedback, the rule was if that section has an odd number of poles and zeros to the right of it, it is going to be in our trajectory. So from -2 to plus infinity, we don't have anything to the right of that section. So this part is not going to be in our trajectory. Between -2 and -5, we have one pole, so this is going to be in our trajectory. And from -5 to -infinity, we have two poles to the right of it, so it is not going to be in our trajectory. Okay, so this is for the real axis. Now, we have two poles and no zeros. Basically, two finite poles and no finite zeros. So we talked about that. If we are short for the zeros, we can assume that, okay, short for finite zeros, let me be clear. We can assume that there are some zeros in infinity that these poles would end up to. Okay, so these poles, the trajectory would start from each of these poles, move toward each other. At some point, they are going to leave the real axis and move to the plus and minus infinity. Okay, now if we have a trajectory to infinity, we said we need to find what part of infinity, because the infinity exists all over the place. We wanted to see exactly where we are going toward and how we are going toward the infinity. What we can use for that was the asymptotic lines. Okay, the number of the poles minus number of the zeros is, in our case, 2, because we don't have any zeros and we have 2 poles. So we need 2 asymptotic lines. Okay, now to know the exact function for the lines, we need the point that those lines will intersect with the real axis and the theta of those lines with the real axis. That way, we know exactly where those lines are. Now, to find them, we had a formula that we said the intersection point is going to be the summation of the poles minus summation of the zeros over the difference between the number of the poles and zeros. So in our case, the difference is 2. We don't have any zeros, so this part is irrelevant. We have 2 poles, minus 2 and minus 5. So it is going to be minus 7. Are we good? So our intersection would happen at minus 3.5. Let's find it. 1, 2, 3.5. So here is going to be the intersection of the asymptotic lines with our real axis. Now, we also need the theta of those asymptotic lines, and we know the theta of those lines was an odd multiple of pi over the difference between the number of the poles and zeros, when this d in the formula would go from 0 to plus minus 1 and plus minus 2 all the way to infinity. And how far we go for the d is based on the number of the lines that we want. We need 2 lines, so we just need to find out 2 theta. Now, for our case, if d is 0, then the theta will gonna be pi over 2 or 90 degrees. If d is 1, this is gonna be 3 pi over 2, which is again 90 degrees. So 1 would not work for us. It's not adding anything for us. Let's go for a minus 1. If we have minus 1, it is going to be minus pi over 2, which is minus 90 degrees. So we are going to have 90 degree and minus 90 degree for the asymptotic line. So these are going to be our asymptotes lines. But we already said these lines basically touches the trajectory at infinity. So what we have is that, okay, when k goes to infinity, okay, we are gonna touch or limit to these lines. But what would happen when those lines were at what point those lines would leave the real axis, okay, and with what degree? Okay, what is the trajectory of the poles? Now, if we have poles on a real axis, the trajectory would be the place of the breakaway, okay, in this example. And we already know that on a breakaway or break-in point, the theta of our trajectory would be 90 or minus 9. Okay, so we know that in breakaway and breaking point, the theta would be perpendicular to the real axis. So we don't need to find the theta of the departure when we have poles in the real axis. Okay, so that's gone. The only thing that we need to find is the breaking point. Okay, the breakaway and break-in point. Now, we don't have any zeros, so we don't have a break-in. point, so we only have a breakaway point. Do you have a question?
Yeah, sorry, quick question. So for when you're choosing the D, is that based on the N minus M or
No.
we select the D?
The number of the theta value, the number of the line that we need is basically the difference between the number of the poles and zeros. Okay, now we are short for two zeros, so we need two line. Okay, so if we need two line, we need two theta. We're starting from zero, moving plus minus one, plus minus two, all the way to infinity. Okay, but we need only two theta. So we are gonna move toward this trajectory of D up until we have two theta.
So it's because you only have two poles, you then have like only
We only need two asymptote lines because we are short for two zeros.
Okay.
Does that make sense? So if n minus m is equal to a, let's say it's a general case. If n minus the number of the poles minus number of the zeros, I put the absolute value because it doesn't matter which one is bigger. Okay. If this is a, that means we need a lines, a number of lines. That means we need a number of thetas.
Okay.
But all of them would intercept, all those a lines, a number of the lines would intercept at same point with the real axis. So we need one delta a, okay, but for the theta, we need the a number of thetas for our a number of lines. Very good. So now we move forward. First zero, if it give us the first theta, if we go to the plus one and you calculate that, it would also give us 90 degree. So it doesn't work for us. We need two different theta. So we go to minus one, and then we have our second theta. We have two lines. We don't need to move forward more than that. Okay. And if honestly, if you move forward, you are going to end up in these two. Okay, so if you put 2, it's going to be 5 pi, okay, which is exactly like pi. You know, you just have 4 pi 2 times circulating the whole display. You know, you're not going to get more than these two, even if you move the D to infinity. Okay. Now, okay, breakaway point. We need a break. Why? Yeah. Breakaway point, okay, which for finding the breakaway point, we said that we need to have the formula that describes K by the SS, okay, and then the max or mean of the local max and mean of those that function would give us the breakaway and breaking point. So max is breakaway, mean is breaking point. Very good. Now let's go over to find the K based on the S's. Now we know that the 1 plus kg should be, if we wanted to have the pole, should be equal to 0. That means kg is equal to -1. Are we good so far? Now, what is kg? Kg is k over s plus 2, s plus 5. Are we good? So that one should be equal to -1. That means k is going to be minus s plus 2, s plus 5. So this is the function that describes the k based on the s. If you take a derivative from this function, you are going to see that the derivative of the function in respect to s is going to be, what is the derivative that I find? Okay, minus 2s plus 7. Okay, we want to put this equal to 0. If that's supposed to be 0, okay, that means s, this would satisfy, the s that satisfies this condition would be minus 3.5. Are we good?
Is that 2s plus 7?
2s plus 7. Do this. This is, let me write that. This one is basically minus s squared plus 7s plus 10. This is this formula, right? The derivative is going to be 2s plus 7. And the minus is in front of it. And if you wanted to do it in a equal to 0, the minus would not change anything. So 2s equal to 2s plus 7 should be 0, which means s is minus 3.5. Okay, now in this specific case, we have kind of like a situation that our breakaway point and the intersection of the asymptote lines are the same. That means the same point that is delta is also the same point as our breakaway point. What that means? That means we start from that point and we are going to end up to that point. Okay, so right now I draw that touches the line, but since we know that the breakaway and break-in point are the same, that basically means that the trajectory would follow those asymptote lines. So we are going to move, we are going to leave the real axis at this point and move exactly over the asymptote lines. Now, if our breakaway point was somewhere else, then that would not happen. So we are going to move from that breakaway line and then end up touching the asymptote lines. This is a special case, okay? Now, any questions so far? Let me move on with this example and basically try to design this specific function for a specific decay coefficient. Or in this case, I wanted to like have a specific range of decay coefficients. So what I wanted to do is I want to have my psi bigger or equal than 0.8. Very good. So we said we can show the psi the points that actually satisfy that psi, for example, equal to 0.1 with a line with a specific theta that starts from the origin is 0 and moves toward the infinity. So we are going to have a line that represent that theta and it starts from the 0 and move away all the way to infinity. Now, we have this line. What we need is to find out what is the theta of the line. So let me show it by phi. That was, because later on we are going to use the theta. So we know exactly what that line is. Very good. Now, in order to find this theta, okay, to find this line, we can do two things. One is to find the theta with the positive real axis, or find the theta with the negative real axis. Either way, it would give us the same line. So I am gonna actually use here the phi for the negative real axis because I want to directly use the tangent rule for this line. Okay, now we know based on the tangent rule that the projection of this line to the real axis is the cosine of that theta or that phi. So we know that the cosine of that phi is going to be our cosine. Okay, now if that's the case, that means the phi is cosine inverse of that cosine. Now, our cosine, the margin is 0.8, so it's going to be cosine inverse of 0.8, which if we solve it, and actually we already solved, is about 36.87 degree. Are we good? Now, we know from the previous discussion about the second order, third order discussion that we have, that the imaginary part and the real part of the interception point with that line could be found based on the fact that the zeros are going to be minus psi omega n plus minus j omega n times square root of 1 minus psi. You remember that? That was minus psi omega n plus minus j omega n over times 1 square root of 1 minus psi squared. That was the formula that we had for standard pole. Okay, now you can find out that if that's the case, okay, if this is the real part, okay, if this is the real part and this is the imaginary part, we can simply say that the psi is equal to minus, like for example, delta over square root of delta square plus omega d square, which is this part, the whole part. Okay, you can solve the values and find out what we're talking. Now, if this is the value, okay, and actually this is the formula that you can have. Another way I wanted to like introduce another way is easier way. We already know that the imaginary value is the sine of this phi, and the real value is the cosine of this phi. Are we good? So basically that means the imaginary part, let's say omega, over the real part, let's say delta, is gonna be the tangent of the phi. Are we good with that? Imaginary part is the projection of this point to this axis, which is the r omega, and the cosine is the projection to the real axis, which is the, like for example, we call it delta. No, the value. We don't care about the j. We want to like find the value. Okay, this is a tangent. Okay, it doesn't matter. You can have a Cartesian plane, x and y. There's no imaginary. It still is a tangent. You know what I'm saying? So now let's let's call, like, if we have this one, we can say that, for example, omega is equal to the tangent of that phi times delta. That's very clear. Very good. Now, in our case, let's call this one M. In our case, the phi is 36.87. That means this tangent, or this M, is going to be 0.75. So omega is going to be 75% of the delta. Are we good? So this specific point is a complex number. The real part is minus theta. The imaginary part is omega. So this one is going to be minus delta plus J 0.75 delta. Are we good? This is going to be the pole. We find that based on the tangent. Now, if we put this value inside of our denominator of the function, we put that minus delta plus J 0.75 delta. This is one of the poles, right? We are going to put that in the denominator of our function, and that should make the denominator equal to 0 because it's a pole for a specific k. Are we good? So, if that's the case, that means minus delta plus J 0.75 delta plus 2 times minus delta plus J 0.75 delta plus 5 should be 0. Very good so far? Any question about that? This is going to be a pole, so it should make the denominator of our function 0. We just put this value as an S, and that equation of the denominator for that value should be equal to 0. Now, if you run like this, if you basically do the plus 2 plus 5 and multiply these to each other, okay? You would end up with a complex number, let's say an alpha plus J beta, right? This multiplication would end up in a complex number. You want that to be 0. Okay? If it wanted to be 0, both real part and imaginary part should be 0. So let's say imaginary. We're going to consider the imaginary part. So if that's the case, that beta should be 0. If you find the beta, it is going to be 0.75 delta times 7 minus 2 delta, and that should be 0. I just did the multiplication and a summation, find the result as a complex number, and I wanted to like just put the imaginary part equal to 0. This is the imaginary part of this whole complex number, and I want it to be 0. Now, if I want that, if I want this condition to satisfy, I can find the delta. 7 minus 2 delta. Let me it very clear. Are you good? If that part is this value is equal to 0, that means it would happen only for a delta equal to 3.5. It could be delta equal to 0, but delta equal to 0 would not add anything for us. So another one is going to be that this term be 0, which make the delta equal to 3 point. Well, let me actually put that. Either delta could be 0 or 3.5 if this one is 0.
So I think I might be missing the significance of alpha plus j beta. Are you saying that like we're setting beta equal to 0 because there's no imaginary
This would end up in a complex number.
yes.
Okay, this complex number should have a real part and imaginary part. If this is equal to 0, both of them should be equal to 0.
And so you're fine.
Okay, so I just focus on the imaginary part here. You can do that for real part. Still work the same. Okay, I focus on the imaginary part. So if both of them are 0, beta should be 0. If I do the derivation, my beta would be 0.75 delta times 7 minus 2 delta is equal to 0. So either the delta should be 0, so it would be equal to 0, or the delta should be 3.5. So this term becomes 0, and we have a 0. Now, you can look at your graph. If the delta is 0, that means we are here, anywhere in the imaginary. If it's 0, actually, since our omega, you remember our omega was 0.75 of delta. If the delta is 0, both of them become 0, so it is this one, which is not in our trajectory. So it must be the other one, which is actually in our trajectory because we know that our trajectory leaves at minus 3.7. So the real part being 3.7 from this for this pole means the real part is going to be minus 3.7, which makes sense. Sorry, this one, 3.5. It is plus, but this S is minus delta plus J omega. Okay, so this is gonna be, this point is gonna be minus 3.5, which makes sense because it is on our trajectory. Okay, now if the delta is 3.7, we have the formula that describes the omega based on the delta. That means the omega is gonna be 75% of that, which is 2.62 radian per second. So this point is actually minus 3.5 plus J 2.62. Now I find the intersection of that line, okay, with my trajectory. Does that make sense? No, I'm not done yet. This is the trajectory, but my design, the variable that I have control over is that K, all right? This is my control value. And I wanted to get that coefficients equal to 0.8, I have to tune this K in a way that my pole become minus 3.5 plus J 2.62. And we know it's symmetric, so we are going to end up also with a conjugate of that. So this is basically the line. So whatever line you have in a positive half cycle, you are going to have the top part, you are going to have the same line in the bottom line, because this also would give you the same value. Are we good? Now, I need to find the K that satisfies the pole equal to that number. How I can find it? Again, very easy. This denominator at that point should be 0. I just put the number that minus 3.5 plus j 2.62 as s and solve the denominator, okay, for the k that makes this 0. We good? So basically the condition is
and the denominator is let's see, s squared plus s.
So the condition is s squared plus 7s plus 10 plus k, okay, then s is equal to minus 3.5 plus j 2.62 should be equal to 0. We good?
Yeah.
Now, if you do that, if you put the s here and do the mathematics and drive the whole situation, then you would find that the k that will satisfy such a condition is, what is my k? 9.14. So with that k, I would end up having the coefficients of 0.8, the damping coefficients of 0.8. Are we good? Now, I don't want equal to 0.8. I want less than equal than 0.8. Okay? When that would happen, which part? For the less k from 0 to 9.14, I have such a condition, or from 9.14 to infinity. You can solve it actually. Let's put number 8, which is less than. Okay, you can put 1, whatever you want. Okay, whatever works for you. Okay, I'm gonna put 8. If I put 8 here, my function becomes s squared plus 7s plus 18. And if it's equal to 0, and I solve that for the s, my s would be minus 3.5. My s is actually s1 and s2 because we have 2. J 2.39. Very good. Now, what is the phi for this? The angle. Like, let's say I have a point, random point in my trajectory, which should be here. This is 0.9, is less than that. So let's get somewhere here. This is the pole that I get. And actually, I could find that. This is 2.3. I made this very bad. So let me redraw that. This one is gonna be 2.62. That means 1, 2, 3 for 3. Okay. This one is 2.39. So it's gonna be it end up very good. Yeah. So this is gonna be my pole for k equal to 8. Okay, this is k equal to 8, then my denominator is that. This is going to be my pole. Now, what is the phi of that? Okay, if I connect a line from the 0 to that point and call this theta, what would be theta? We know that the tangent of that theta is going to be 2.39 over 3.5. Why I don't put this minus? Anyone can point out? but the value is minus. Why I didn't put the minus? The reason is that I define the theta between line and minus real axis, not the plus real axis. If you do the plus one, then you should include that minus sign too. Now, you can solve for the theta with that function, and you know that your psi is cosine of that theta. Okay, now if you do that, find the theta. Did I find the theta exactly or not? You can solve it. I didn't solve that for theta, but if you solve for theta and find the cosine, it would become somewhere near 0.825, which satisfies my condition. It is bigger than 0.8. Makes sense? If for K8, I would reach to the psi less than 0.8, then this part would not satisfy my condition. But since I chose a random K, okay, less than 9, and it satisfies, that means this part of the trajectory would satisfy the design that I target. Are we good? Any question?
I like a fan method, like, okay, I take a case 1.5 K to 15.5. In that case, I think.
Yes, this is easier way. You can have a general kind of like situation when you have your function of the K based on the S. Okay, you can find out where it's goes bigger than 0.8 or when it goes less than that. But that would have like a very crazy kind of like derivation, formal derivation. This is easier. And it's not just 8, you can just put 1 or 2, or whatever works for you. Anything less, or even you can go bigger. Okay, if you go bigger, you would find out that if you move further than that K 9.14, then you would not satisfy. So that means this is a margin, it should be less than that. You know what I'm saying? So, okay, are we good? Any question? If you find it better example that I have here. So, what did I do there with Harrison? Up here. Okay. Let's go for another example. In the next example, we are going to have a specific function for our open loop transfer function. And we are going to try to sketch again the root loops. Now, in this example, I want to give you GH instead of the G. And my GH is K over S times S plus 1 times S plus 2. Let's sketch the numbers. So we have 0, 1, 2, 3, 4, 1, 2, 3, 4. And we don't have anything in the positive real axis, so let's move on. Good. First step, put the poles in, zeros and poles. We don't have any zeros, so we just wanted to like put the poles. One pole is at 0, another one is at -1, and another one is at -2. Now, finding the real axis section that include our trajectory. Here, we don't have anything to the right, so no. Here we have 1, so there is going to be a trajectory here. Here we have 2, so into the right, so no. And here we have 3, so we are going to have a trajectory here. Now, the difference between the number of the poles and zeros is 3. Actually, we don't have any zeros, so we are short for 3. So that means we are going to end up in 3 asymptote lines. Okay, so n minus m is 3. So we need to find our delta A, which was the poles, the summation of the poles minus the summation of the zeros over that n minus m. We are going to have, we don't have a 0, so that's gone. We have 0, -1, -2 over 3, which is -1. So add -1. At -1, I have, this is also my delta A, -1, -2. So this, at this pole, I have my asymptote crossing the real axis. Good? Now, I want the theta's. The theta's was 2d plus 1 pi over that n minus m, which is, this is 3, I'm gonna just write 3. And I'm gonna go d equal to 0, and then plus -1, and plus -2, all the way to infinity until I get my 3 theta that I want. So if it's 0, it is gonna be, if the d is 0, my theta is gonna be pi over 3, which is theta A1 is gonna be 60. If I have d equal to 1, it is gonna be 2 pi over 3. So my second theta is going to be 180. And if it d is -1, it is going to be minus pi over 3, which is -60. We good? So here, I am going to have 3 asymptote lines. 60 degree, -60 degree, and another one at 180. The 181 is quite clear. So it's the trajectory of my third pole. Okay? But these ones, we are going to have 2 asymptote lines that we know we are going to end up. Good? So we know we are going to end up here. Now, what is the breaking point and breakaway point? Again, this one, this GH should be equal to -1, which basically is KGH, but my K is inside the GH. So that means k over s, s plus 1, s plus 2 should be minus 1. That means my k is s cubed plus 3s, right? Plus 3, did I make it right? S cubed, and then 1s, 2s, 3s, plus 1s and 2s, 3s squared 3s. Did I write this? Oh, 2s, sorry. 2s plus k equal to 0. This k is already over there. So it's equal to 0, and this is a minus sign in front of it. So my dk over ds is going to be minus 3s plus 6s squared 6s plus 2, and this should be 0 for max and mean kind of a calculation. So if I do that, what are going to be my s's? The s's are going to be s1 and s2 are going to be minus 0.42 and minus 1.58. Okay, one is mean, one is max. Since 1.58 falls in this section, which is not in my trajectory, so that means this one is the breakaway. So it's 0.42, so it's going to be somewhere here. Very good. And we are going to leave the real axis in 90 degree. So we are going to end up with this trajectory. Let me draw it with the same color. Very good. Now, what else we need to find out in order to find the exact, to have exact a sketch of our Locus? Any idea what we are missing to have the exact trajectory, the exact graph for the trajectories? Anyone remember that? What point here you don't have? This is the pole, you know, there they are. The theta's and trajectory, you know. This point of breakaway is minus 0.42. What point in this stochasticity, in this trajectory, you don't have yet? Anyway, look at this trajectory. Go ahead.
Any holes? Wait, no.
You're in the right track. The only point that we're missing is the point that the trajectory would cross the imaginary line, because that point would give us the margin of the stability and instability. Very good. So, do you remember how we would find that poke, those points? We would have to create the Routh-Hurwitz table and create one of the rows equal to 0. Then the row before that would be the function that describes those poles, or the roots of that function would be the poles on the imaginary axis when we cross the imaginary axis. Is that clear? So we already derived the characteristics function, which is the denominator of the whole transfer function. Let me actually write the transfer function. It is going to be k over s cubed plus 3s s squared plus 2s plus k. This is going to be our TS. So this is our denominator or characteristic equation. Now we want to write the root Hurwitz for that equation. Is third order, so we have s cubed, s squared, s, and s to the power of 0, which is 1. Very good. Now, the first row was the first component of the first row was the coefficients of the s squared, which is 1. We skip 1, then we have 2. Then for the s squared, we have the first component is the coefficients of s squared is 3. We skip 1, and then we have k. Now, you know how to find the B1, B2, C1, C2. We already did the formula. So if you do that, this one would become 6 minus k over 3, and this one becomes 0 because we don't have anything here. And the last row would be k. Are we good so far? Now, first column is constant number. We cannot make it fully 0. Okay. Second one, it has one constant component, positive constant component. We cannot make that second row 0 too. This one would give us a chance to have a 0 line. For what? If Rk is equal to 6, then the whole row becomes 0. Very good. Now that we have a k that makes this S row, the first order row, 0, we can put that k into the second order, the line above it, and find the exact formula of the second order line, which is going to be, therefore, the second order line is going to be 3s squared plus 6. If it's equal to 0, we want to find the roots. Okay, that means it's basically these two cancel each other out. If it's equal to 0, so it's basically s squared plus 2. Okay, so the s1 and s2 are going to be plus minus j, the square root of 2. Right? Any question? That means these 2 points, that would basically trajectory would cross the imaginary line are going to be j square root of 2 and minus j square root of 2. Now we have the full accurate trajectory of our poles, and we use the root Locus to draw it. Any question? Good. Yeah. Now I want to ask a question. We know the trajectory, and we know it would cross the imaginary line in plus minus j square root of 2. That means those are the margin of stability and instability. So how we can find the k in our system. So we know what part of like the margin of the K that would keep our system stable. So we could avoid increasing from that point, increasing the K from that point and move to the unstable situation. How we can find those Ks? Wait, that's good. Two-way. You already have the Lutherwitz, and you know the condition of the stability in Lutherwitz was that this first column would not change polarity. So if 1 and 3 are positive, K and 6 minus K over 3 should be also positive. Otherwise, it's unstable. So you would find, now, we know that K will start from 0 and go to the infinity. So this one is positive. The only question is this one. For K equal to 6, this one becomes 0. For K less than 6, what would happen here? It would be positive because less than 6, the denominator is positive. The denominator also positive, so this remain positive. Okay, if we go further than 6, then the denominator will become negative, so we are changing polarity. So that means our stability condition is when the K is between 0 and 6. If we go further than 6, we are losing stability. Very good. Now, that's one way to find it. The next way is that you know the poles that crosses the J omega. Okay. Very good. Now, this is the characteristics equation of our system. Any complex number beside these, like to the right of these imaginary axis, let's say here, would be a complex number of like delta plus minus, this is plus, minus 1 is here, plus J, some like, let's say alpha and beta. Right? This is a complex number in S. Now, if you put that complex number into the characteristics, again, if you remember from the last example, you are gonna end up with a specific complex number as a result of this function when S is equal to alpha plus J beta. Okay, and it is a pole, so this should be 0. The whole complex number should be 0. That means the imaginary number or real part of that should be 0, the resulting complex number. So here you have S cubed plus 3S squared plus 2S plus K. Okay, when S is equal to alpha plus J beta, you are going to end up, if you put this, you are going to end up with a complex number, okay, that is a function of K. K is in that complex result, right? So you are going to end up, for example, of a function of K in a real part plus J, a function of K in a imaginary, right? That should be 0 because this is a pole. It should be 0. That means this should be 0. And again, like before, if this is 0, that means real part should be 0, imaginary part should be 0. You can focus on either one of them and find the K. So, for example, K is equal to 10. For example, okay? Then you know that the K 10, which is bigger than that 6, which gives you unstability. So the margin, if we go further, you are unstable. Now, In this case, it's actually very clear because we know that the K starts from the pole and end up with zero, or zero is in infinity. So we know if we wanted to have to stay in the left hand, okay, K is increasing, okay, K is increasing. So if we wanted to stay in the left hand, then we should be K should be less than a 6. It is obvious, but if you have a more complex kind of like situation, okay, marginally stable. If you have more complex, then you can use either one of these conditions to find out where you end up in stability and where you end up in instability. Are we good? Okay. Any question? So today we practice how we can sketch an exact root locus, and also we practice how we can design our system. Our variable is K. That's the variable that we have control over. How we can design our system in a way that we end up with a specific targeted damping coefficients, okay, and get to our desired system. Now, we said damping coefficient is one of the characteristics of system. Another one could be overshoot, but we already covered that in previous session, how we can translate an overshoot to the damping coefficients. Are we good? Now, any question? No? Okay, so that's it for today. If you don't have any question, we can end this discussion and have a great rest of the day.